Some words in mathematics are dangerous. In this video, the dangerous word is random. Because when most people hear random, they imagine a coin toss. Heads or tails. One flip, then another. The next flip does not care what happened before. If you got heads 5 times in a row, the coin does not remember. The 6th flip is still just a flip. That picture is useful, but it can also be misleading. Because not every random process is like a coin toss. Tomorrow's weather depends on today's weather. The next word in a sentence depends on the words before it. A piece in a board game moves randomly, but where it can go depends on where it already is. So here is the question. Can something be random, dependent, and still mathematically predictable? For a long time, probability was most comfortable with independence. If one event does not influence another, calculations become clean. If a fair coin has probability 1/2 of landing heads, then 2 heads in a row have probability 1/2 times 1/2. That is the old coin flip world. Each trial is separate. Each step begins fresh. And in that world, one of the central ideas of probability becomes visible. The law of large numbers. Flip a fair coin 10 times, and the result may be messy. 6 heads, 4 tails. 7 heads, 3 tails. Maybe something even stranger. But flip it many times, and the proportion of heads tends to settle near 1/2. The short run jumps around. The long run becomes stable. Jacob Bernoulli gave one of the first rigorous forms of this idea in the early 18th century. And for a long time, independence sat near the center of how people imagined probability. But then came a dangerous inference. If independent trials can produce stable averages, does a stable average mean the trials must be independent? That sounds plausible, but it is false. And this false step became part of a strange mathematical dispute in Russia. Pavel Nekrasov was a mathematician who connected probability with a much larger claim about human freedom. He looked at social statistics, marriages, births, crimes, and other large-scale human data. These numbers often showed a kind of statistical regularity from year to year. Nekrasov took this as evidence that the individual decisions underneath them behaved like independent events. And from there, he connected the mathematics to free will. Andrey Markov thought the mathematical inference was wrong. His objection was not simply political or philosophical. It was mathematical. Seeing long-run regularity does not prove independence. A system may be dependent and still settle into stable averages. So Markov needed an example. Not a coin. Not dice. Not anything where each trial obviously starts over. He needed a chain. And he found one in poetry. Markov turned to Alexander Pushkin's Eugene Onegin, one of the central works of Russian literature. But he did not read it as literature. He treated it as data. He removed spaces and punctuation. He looked at the first 20,000 letters. Then he reduced every letter to one of 2 types, vowel or consonant. At first, this sounds almost absurd. A great poem becomes a long string of V's and C's. But that simplification was the point. If the letters were independent, then knowing that one letter is a vowel should not tell you much about the next letter. The probability of a vowel after a vowel would be roughly the same as the probability of a vowel anywhere. But that is not what Markov found. In the text, about 43% of the letters were vowels. So if letters were independent, 2 vowels in a row should appear about 43% times 43% of the time. That is about 19%. But the actual number of vowel-vowel pairs was far lower. The letters were not behaving like independent coin flips. They were linked. A vowel made another vowel less likely. A consonant changed what was likely to come next. The next symbol depended on the current symbol. And this was the opening. Markov drew the situation as a system with states. One state for vowel. One state for consonant. From vowel, the next letter could be another vowel. Or it could be a consonant. From consonant, the next letter could be a vowel. Or it could be another consonant. Each arrow had a probability. This was not a sequence of isolated events. It was a chain of transitions. The system did not need to remember the entire poem. It only needed to know its present state. If you are at a vowel, use the vowel probabilities. If you are at a consonant, use the consonant probabilities. That is the core idea of a Markov chain. The next step is random, but the probabilities depend on where you are now. This is why the word random is dangerous. Random does not mean independent. Random does not mean patternless. Random does not mean impossible to analyze. A Markov chain is random with structure. It remembers the present. It forgets the path. That is a strange kind of simplification. And it is powerful, because many real systems have long histories. A weather pattern has a long history. A sentence has a long history. A game position has a long history. A web page is part of a huge network of other pages. In principle, you could try to trace everything. But Markov's idea says that, for some systems, you do not need everything. You can build a useful model from the current state and the probabilities of moving to the next state. This does not solve every problem. It does not make prediction magical. It does not say that the past never matters. It says something more precise. If the current state contains the information needed for the next transition, then the whole earlier path can be ignored for the purpose of the model. That is the Markov property. And once you see it, the world begins to look different. A board game becomes a map of possible positions. A text becomes a chain of symbols. A network becomes a system of pages and links. A random walk becomes a way to measure where you are likely to end up. This is one reason Markov chains later appeared in so many places. In early text prediction, the next letter or word could be chosen from probabilities based on earlier symbols. In PageRank, the web could be imagined as a random surfer moving from page to page through links. The pages are states. The links are transitions. The long-run behavior gives information about which pages are more central. These later systems are more complicated than Markov's vowel and consonant model. Modern search engines and modern language models go far beyond simple chains. But the conceptual turn is still there. Probability no longer had to live only in the clean world of independent coin flips. It could enter systems where the next step depends on this step. It could study randomness with memory, or more exactly, randomness with limited memory. And that was the point Markov needed. Nekrasov had looked at stable averages and tried to infer independence. Markov showed that this inference was unsafe. Long-run order does not prove independent causes. A dependent chain can also settle. So the poem was not just a poem. It became a counterexample to a way of thinking. The old question was, how do we calculate probability when events are independent? The new question became, how do we calculate probability when events are linked? That question opened a new structure. Not isolated events. States. Not separate trials. Transitions. Not pure chaos. A chain. So the next time something is called random, be careful. Ask what kind of random? Independent random? Dependent random? Random with a changing state? Random with a long-run pattern? Because in mathematics, random does not always mean free from structure. Sometimes, random means the structure is hidden in the transitions. And behind those transitions is one of the simplest and most powerful ideas in probability. The next step may be uncertain, but it may not be independent. For more stories behind the ideas that shaped mathematics, subscribe to Behind the Theorem.